Is my audio clear now?
Somewhat better.
Okay. Professor Susmita Shor Kolay is a faculty member at the Advanced Computing and Microelectronics Unit, Indian Statistical Institute. She received the BTech degree in Electronics and Electrical Communication Engineering from IIT Kharagpur and the PhD degree in Computer Science and Engineering from Jadavpur University. She was in the laboratory for computer science at Massachusetts Institute of Technology as a graduate research assistant, a postdoctoral fellow at the University of Nebraska-Lincoln, a reader at Jadavpur University during 1993 to 99. She was a visiting faculty member at Intel Corporation USA in 2002 and 2005, a visiting researcher at Princeton University in 2012, INSA visitor in U Bremen in 2016. Her research contributions are in the areas of algorithms for design, automation of secure electronic systems, and reliable quantum computers, graph algorithms. She is a fellow of Indian National Academy of Engineering and, among other awards, a recipient of the President of India Gold Medal, a Distinguished Alumnus Award of IIT Kharagpur, and Women in Technology Leadership Award of the VLSI Society of India. Ma'am, you can please start your session now.
Thank you very much for the kind introduction. Let me just share the slides. Is it visible?
Yes, ma'am, the slide.
Okay. So, good evening to all the attendees. There's still a lot of echo. I don't know how to stop it. Anyway, I'll continue. So the agenda today is we'll take up 3 key algorithms which sort of set people to look into quantum computing very seriously. The first one is one of the earliest ones. It's called the first one is actually Deutsch's algorithm, and then it was appended or sort of improved and extended along with Jozsa. Okay, so 3 algorithms only, and it's been a long day for many of you. So let's try to keep it simple, but get a sense of how this is different from the kind of classical algorithms we are familiar with. So the major drivers you have already known is that we have sorry, this seems to be so there seemed this provides, as opposed to classical, the superposition provides parallelism, and reversibility actually is very attractive because of the energy crisis or power dissipation crisis which semiconductor technology suffers from. So we know the history that Alan Turing proposed the Turing machine, and about half a century later, Richard Feynman gave us the first ideas. So with the Turing machine, the idea of stepwise computing, the idea of an algorithm, the idea of a machine to do the computability came along. And Richard Feynman told us that by using quantum mechanics to do computing, we can do massive computation. In fact, I'll share the lecture at which Professor Feynman stated this. I was present at that lecture, but I did not grasp the essence of it then. It was almost 20 years later that this came upon me. So David Deutsch came up with very soon in 1985, came up with the first quantum uh, sort of machine and the algorithm, and then Peter Shor's factorization algorithm, which put the public key cryptography system of RSA uh, at stake. Although even today, all the e-commerce that you do is based on RSA. And when we discuss this, I'll tell you why we still are using RSA. And then the experimental physicist went on working to actually realize quantum uh, computers, which was recognized by a Nobel Prize in Physics in 2012. Now, just to have an idea, Deutsch's oracle problem of 1985 was that you're given a classical black box Boolean function, which means there is only one bit as a unit, as the input, and one bit as an output. Can you tell whether um, the two possible values of inputs for those two values, the value of the function is same? That is, the function is a constant function. And classically, what will you do? You will compute f0, f of 0, and f of 1. So two evaluations. But can I answer this question by evaluating only once? Not classically, but in quanta. And then if you extend this to a Boolean, n variable Boolean function, of course, you would need a lot more evaluations classically, but in quantum, you can do much faster. So this actually gave us the first hint that quantum computing can give us a lot of speed up over classical. Shor first in 1994 and then 97 he improved it a bit, gave the algorithm for factoring. So here's an example. Suppose I had 50 digits. I have an integer with 50 digits. In classical machines, it would take about 1 second or so to factorize. But in quantum computing time, it may take a lot of time because this has come down, but still you have to set things up and repeat, so on. As the size increases of the input, we find that the time for the classical time increases from 1 second to 2.5 days. Just doubling the size of the input increases the classical time quite a bit, but not so much the quantum time. And so on. If you go on for an integer with 2000 digits, then classically we won't be able to get the correct answer. I mean, we won't be there to see, but with quantum, we can do better. Okay? So similarly, the for search, we do get improvement, not exponential, but uh, quadratic improvement. A lot of algorithms have been designed since then, and I would really encourage you to visit this particular website called Quantum Algorithm Zoo, which lists all the algorithms designed till date. So this was the classical this is the Deutsch-Jozsa problem for the n variable Boolean function, as in, so you have as input n bit strings of length n bits and only one bit as an output. This is how I write the function. This is of course, a non-reversible function, because reversible functions have the same number of, same size of the input as the output. So if you have n bits in the input, you would, in a reversible function, you will have n bits in the output. So that by looking at the output, you can uniquely say what was the input. That is the notion of reversibility. Now, we don't know what the function is, but we are only given the information that the function is either constant or balanced. By constant, I mean for all the possible inputs, here there are 2 to the n of them, the value of the function is the same. And by balanced, I mean that, as is shown in this figure, that for half of the inputs, we don't know which half, the value of the function is 1. For the other remaining half of the inputs, the value is 0. So this much we know. But the question we want to answer is this black box function constant or balanced? And in order to do so, how many times do I need to evaluate this function? That means call the black box to do the evaluation, feed the input, and observe the output. So classically, uh, we would need at least 2 to the n minus 1 plus 1, which means that if all of these values for the output for the function are same, then we can say it's a constant. And if at least one, I mean, if one is different, then we know it's a balanced function. So the number of times we have to evaluate, which gives the query complexity, how many queries you make, is this much in classical. One other option could be that you just randomly pick 2 input values, okay, and feed it to the black box. If the output values are equal, then you guess that it's constant. Otherwise, if they're different, then you say it's balanced. So what is the probability of a wrong answer? So are these many are the total possibilities. Of them, only these are the ones for which it may be different, and that probability turns out to be less than half. So in some sense, uh, we can bound the error, the probability of error, for even with classical query complexity using randomization. But if I do not want any error, can I do it? So let's look at the key idea. So first take the Deutsch's algorithm. Let's take the Deutsch's algorithm, where you have just 1 bit input and 1 bit output. Okay, you can see there are only 4 functions for which it could be either a constant or a balanced. And classically, as I said before, you would need 2 evaluations of the function. What about quantum? Now for quantum, we can set up something like this, that we have some uh, a qubit in the state Qiskit and another qubit in the state Yk, and you have a unitary based on this unknown is black box function. For the moment, just assume that somebody has given you this. Okay? And the output you define is as follows, that the top qubit remains unchanged, and the bottom qubit is the XOR, which is the addition modulo 2 of the value of the second qubit and the value of the function on the x value. Okay, so now what do we choose x and y to be so that we can for sure tell whether the function is constant or balanced? So suppose I choose both x and y to be 0k, and I add a Hadamard operation. I presume you know what Hadamard is. It creates equal superposition. So if you have 0 ket, apply Hadamard on it, you would get 0 ket plus 1 ket divided by root 2. And the second qubit remains as it is. Okay, and you feed it to this unitary function, and then check what happens over here. You do the uh, math over here. So we know that the output function here can be written as the so this is the input, and then you had one Hadamard and the identity gate, which is this one. So this is the tensor product because you have independent parallel system. And finally, you apply the unitary for F. So this is in reverse order. You can do matrix multiplication, chain matrix multiplication. And once you do that, you will get this as output. So what will happen is the X will be, so X, if you measure after this, either on both the qubits, you find that there is equal probability of getting a 0 and a 1. So there's no way you can distinguish or say anything about the function. Next, let's try something else, that we just set the second qubit to 1 and add a Hadamard on the second qubit only, just before the unitary. So with this, the output function would look like this, right? You have identity tensor H, okay? And if you do the math, then you will find that the output will look like this. So what does this say? This says that the top qubit remains unchanged, but the bottom qubit, if you measure, has equal probability of getting a 0 and a 1. Still not good enough. But I can combine the idea of these two and do the following. I In the first attempt, I had a Hadamard here and a Hadamard here. In the second attempt, I had a Hadamard here, and I had 1 ket on the second qubit. Okay, so therefore, the output that you get over here is given by this expression. Okay, so you have a 0 ket, 1 ket, and you have the two tensor of these two Hadamards. Then you have the unitary, and then again you have I tensor H. Okay, and if you do this the matrix multiplication, the matrix vector multiplication, you will get this over here. So if F is constant, actually what you will get on the top qubit is always a 0, which I was not getting over here. And if F is balanced, then of course I will definitely not get a 0. Okay, I'm just measuring the top qubit. So if I get a 0 on the measurement, then I can definitely say that F is constant. and I'm doing only a constant number of operations. Okay, instead of 2 to the n minus 1 plus 1. So that gives us an idea. This is for two elements, and I will generalize this as follows for n qubits and one extra qubit over here. And we have this sort of a thing, same as over there. So there were two tricks. The one is known as the phase kickback, that is converting the amplitude to the phase. And of course, I did superposition. Okay, so the phase kickback is that if it gives you that if the function is constant, when you measure, it's the zero get all zeros at the state. And if it is balanced, then R will never be zero. Therefore, I can answer this with one quantum query. So the phase kickback idea, I mean, is that instead of we had um, we had the amplitude of f of x, and I mean f of x was affecting the amplitude, but because of this Hadamarding of the last qubit, what we could get is that now it's the phase which is being determined by the value of the function. Okay, so therefore classical query complexity was this much. Bounded error classical complexity, as we saw, was constant, but it did have error. But the exact quantum query complexity is 1. Okay, so therefore we get an exponential speed up with this particular quantum algorithm. Now you might say that this is in some sense somewhat a concocted problem. Okay, so let's move on. But then we did get exponential speed up, so that led scientists and researchers to explore other problems where we could get speed up over classical method. So what's Grover search related? So this is an unsorted, this search is for an unsorted list. So I have a list of elements, capital N elements, okay, and I'm given one element and asked whether that element belongs to this list. Sorry for this flickering. I don't know why this is happening. Now, since if had this been sorted, we could have applied binary search and we would have got the answer in big O of log of capital N here. Okay? But this is not sorted, so therefore I have to keep looking at all the entry. Now I can encode this in the quantum domain, that corresponding to the values in the list, I have the states of the quantum system, and the function that I have defined is such that if so S new is the state I'm trying to identify or search in the list. So all the states in the list, that is all the occurrences of S new, if for them the characteristic vector for that particular state has a bit 1, and for all others which are not equal, it is 0. So for an unsorted list of 2 to the small n items, we can represent this with a 2 to the n plus 1 times 2 to the n plus 1 unitary squared matrix, and let's call this UC. So here's an let me just first illustrate. Uh, yeah, first illustrate the idea of Grover search. That is, how am I going to reduce from capital N to order square root of capital N? So assume you have an unsorted list and I'm searching for the second one. Although this looks like one, two, it looks like sorted, but we don't know whether it's sorted. Now what I have a mechanism to negate the target value. Okay, so the list now becomes like this. Now take the average of these values, and I find that the average becomes 5.5. And I deduct the value of this average from each of these list entries, and now the list becomes this. Next, again, I negate the value entry corresponding to the marked I mean the one that I'm trying to search. So now the list becomes like this. So notice I'm somehow amplifying the value of the one that I'm trying to find. Okay, and if I take the average now, this is the average, and again I repeat the same thing. Now the list becomes this. So you see, the value that I'm trying to find has been increased from all the other values. Now, how is this relevant? Remember, uh, we are in a quantum system. Uh, Ultimately, we make a measurement, and even though if we have all the values present, we will get only one of the values. It collapses to one of the basis states, the pure states, possible states. So we are trying to increase the probability of the state corresponding to the correct answer. That is always the key idea behind designing any quantum algorithm. Now the question is, how many times do I repeat this negation, that is called inverting the phase, and taking the average, which is known as the diffusion? How many times do I iterate on these two operations? That before I take the measurement. That is the key calculation that Grover made. Another illustration, we had all equal values. Even then, you find that after a few iterations, the separation between the amplitudes happen. Okay? So the unitary function that I talked of, if I have capital N as 4, then I will have, so small n is 2. And remember, this would have been a 2 to the small n plus 1, which is 2 to the 3 times 2 to the 3 matrix. Okay. And if I know that for the value 1, 0, that is the marked one, uh, the the condition is 1 and 0 otherwise, I can represent this unitary function by this matrix over here. Now, we did the invert of phase, which is like the rotation. Okay, rotation. So this matrix, unitary matrix here, corresponds to the rotate phase operator when it's the marked state which has the -1 entry. And then we had the averaging and taking the deducting from the average. Okay, so this is known as the diffusion operator. So first we inverted, and then we did, so this was the average, and after we did the deduction, the values of all others decreased, and the value of this, because I'm taking a minus of a minus, it gets added and it is increasing. So the algorithm goes like this. You take a small n number of qubits, a register, so that this applies. And after you do a Hadamard operation to get equal superposition, then you alternately apply the rotation and the diffusion, and then you measure. So uh, there's another slide. So we can show that what we are having over here is first uh, the unitary function, and then these two iterations. Okay, so these two, uh, just 1 minute, let me just get out. No, I don't have it. Okay. Um, Sorry about this. So we can show that the average amplitude would be this, and after addition, you would get this. So let's say I want k iterations, then because this is the amplitude, if you these many iterations, then you would get to, you can increase the amplitude to 1, and you can do the exact calculations and find that this is what you have. So that is why, because you are doing these many iterations, the complexity of Grover's algorithm reduces from the classical big O of big N to big O of square root of N, which is again a speed up. Okay. In the interest of time, I will now move on to the Shor's factoring algorithm. Well, before that, this Grover search algorithm is a very generic algorithm. You can look at any algorithm that you have. You have some input, you have corresponding output depending on the problem, and the output, the correct output, the algorithm design is done to search for the correct output. So any algorithm design can be thought of as a search algorithm if you have an optimization or some sort of problem. So depending on what the UC is, you can have uh, Grover's formulation for that problem. Sometimes Grover's will be more efficient, just as in this case of unsorted element search, and sometimes it will not be, because you will be able to devise another quantum algorithm which would be better, which will give you better speed up than Grover's algorithm. For example, the factoring algorithm is also a search problem, because you're searching for the factors. What you can do is you can check divisibility by numbers going from 2 to, or maybe 3 to the square root of whatever integer you want to factor. Okay, the question is how many iterations I will have over there, which will be square root of, so n to the power 1/4. Okay, but that is not polynomial in the size of the input. Be very careful. You are feeding in one integer. If the value of the input is capital N, then the size of the input is log of capital N. Whereas Grover search would need n to the power capital N to the power 1/4. So therefore, capital N to the power 1/4 is exponential compared to the size of log of capital N. That's why Grover search does not give you exponential speed up for factoring, but Shor does. Now let's see what the idea of Shor's factoring idea. So in 1994, Peter Shor, the mathematician, uh, gave up. So just as in all the idea, all these algorithms I've described, so all the previous two algorithms, the idea is very simple, something which is very primitive. It's only that how we implement it once we get the idea. Same with Shor's. So here is an example of a 175 digit integer, which has been factorized to two 85 digit integers. Classically, a factorization takes e to the power, I mean, it's exponential in n to the power 1/3. It could be 2 to the some constant times n to the power 1/3, where n is the number of is the uh, value of the integer. No, I'm sorry. A small n is the number of digits in the integer. Now, Shor's quantum algorithm, which we will discuss now, takes n cube times log of n. So the value of the integer was 2 to the n, represented by small n, 2 to the small n, represented by small n number of bits. And therefore, this is polynomial in the number of bits, the input size. That's so in 1994, when this algorithm was proposed, that is when everybody sat up and started thinking, how can we have the circuits or the real implementation to do quantum computing? Okay, what is the idea? The key idea is very simple. It is based on an important number theoretic result. So I have, let's say I have a function defined on integers, which is x to the power a, x is an integer, modulo another integer, capital N. And here x and n are relatively prime, that is, they do not share any factors. Now, this function has been shown that these will be this type of function will always be periodic. What does that mean? So suppose capital N is 21, I choose x to be 2. So modulo n, so 2 to the 0 is 1, uh, then 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, modulo 21 remains 16. So up to 4 modulo operation, I mean, these are all less than n. When you get to 5, which is to 32, so 32 modulo 21 is 11. And the next one, 64 modulo 21 is 1, which means that 2 to the 0 was 1. So 0, 1, 2, 3, 4. And when you get to 5, 6, you again repeat this pattern. Okay, that is 1, 2, 4, 8, 16, 11, and then again 1, 2, 4. So the periodicity is 6. Now, what does that mean? That means If r is the periodicity, then x to the power r modulo n is equal to 1. R is an integer, and typically this is because this can be a this will be an even integer. So then I can define r by 2. So let's call x r by 2 modulo n to be y. So in this case, y happens to be 8. Now if I take the GCD of 8 minus 1 and n, and 8 plus 1 and n, I get 7 and 3, which are the factors of 21. Now, this is not magic. This is just middle school or primary school arithmetic. Why? Because this is what y was. Okay. And so, therefore, y square modulo n, because r by 2, y has r by 2, and y square would be multiplying this with 2. So I'll get x to the power r. So that is equal to 1. Now y square modulo n is same as y square we know is y plus 1 times y minus 1 modulo n, that is equal to 0, right? Because y square minus 1, I took the 1 out on this side, and therefore modulo n would be 0. Now what does this mean? That means that this capital N divides or shares some factors with y plus 1 and y minus 1. That is why it cancels out and we get a 0. So if I take the GCD of y minus 1 with n and y plus 1 with n, I should get the non-trivial factors of n. That is why this worked. So this is not magic, this is number theory, and pretty simple number theory. Then you might wonder, why weren't algorithm designers, why didn't they come up with this idea and have an algorithm for factorization? Well, the catch is, how do you find R? That is what was taking classically exponential time. And sure that you can do that in polynomial if you use quanta. Now I'm running out of time, so I'll race through a little bit. So what you do is, you want to factor an odd integer. So just to illustrate, I'll choose 15, a simple one. To check whether it's prime, we already have a polynomial time algorithm by Manindra Agarwal and his students. We can check whether it's an even number, dividing by 2. We can also check whether it's an integer power of a prime. So we exclude these cases uh, and not apply quantum, okay? Because there are classical methods to check all this and provide factors. So then, since it's not prime, it's not a prime power, it's not even, what we do is we choose an integer which lies between capital N square and twice capital N square. So Q was, capital N was 15. So 225 and 450, let's pick 256. This happens to be a power of 2 for simplicity. And I also choose a random integer x, which is relatively prime to n, and we can pick 7, let's say. It's better to pick an odd integer. Why are we doing this? Now, we will create 2 quantum registers. These registers must also be entangled so that the collapse of the input register corresponds to the collapse of the output register. So this is where one of the important quantum phenomena, which is not there in classical, is being used. So what does the input register contain? It contains enough qubits to represent numbers as large as q minus 1, in this case up to 255. So it will need 8 qubits. And the output register contains enough qubits to represent numbers as large as capital N minus 1 in this case 14, so 4 qubits suffice. So we initialize the input register with an equal superposition of the integers from 0 to 255, and the output register is all zeros. So therefore, the total state is like this. Okay, and this shows that they are entangled. So now we will apply, because all of them are all possible values here are um, present. We will apply x to the power a modulo n in parallel to the input register, all possible states in one, and so the output register will contain these values, and you can notice the periodicity of 4. Okay, next step is to measure the output register, and this will collapse to just one of the results of the transformation. Let's call this value C, which means it will collapse to one of the following 4 values. Let's say it collapses to 1. Okay, now things are getting interesting. Since the 2 registers were entangled, measuring output register will have the effect of partially collapsing the input register into an equal superposition of each state between 0 and q minus 1 that yielded C, only the one corresponding to whatever was measured in the output register. So you get 1/4 of the 256 states. Okay, so the probabilities are now equal superposition of, instead of 250, now you have 64 values. And this is where the actual quantum operation takes place, which is the quantum Fourier transform on the partially collapsed input register. It takes a state A and transform it into a state like this. Okay, so in this case, in the running example, this will collapse to something like this. So the set of all values that have 7 to the power a modulo 15, which yielded 1, these are the values that you will get over here. So these are the states that you would see, and after QFT you will get something. So these technicalities you can work out later, but what will happen is that this QFT will essentially peak the probability amplitudes at integer multiples of Q by R. Q was 256, R was 4. Now we are trying to find R, but multiples of Q by R, we know Q, we know the multiples of Q by R, and so by measuring we'll get one of these states. Let's call this value R, and it will be a multiple of Q by R. So knowing Q and knowing M by methods of calculating, let's say for example continuous fraction expansion of the ratio, we can find out R, the periodicity. And this was done in polynomial number of steps. Even the QFT happens in polynomial number of steps. FFT also we can do. Okay. So once we get the R, then the rest is easy, right? The GCD, etc., is polynomial time. Okay, this can be done on the classical computer. So if the Shor's algorithm fails, when will it fail? One is when the QFT will uh, come up with a wrong period. Somehow the calculation didn't happen. This probability is actually dependent on your choice of Q. The larger the Q, the higher the probability of finding the correct uh, period. Okay. Another case could be somehow by your calculation, the value of the R turns out to be odd. Then R by 2 cannot be computed. Okay. Or another case could be the Fourier transform measured to be 0. Therefore, with 0, if m is 0, then you cannot find out r from q. Okay. Uh, or if the algorithm finds the factors are 1 and small n, that is also not useful. So in these cases, what do? You pick a new x and repeat. Okay. So Shor's feat was that in classical machine, what was done is 2 to the capital N time steps. With a quantum algorithm, he reduced it to NQ. Now, why are we still using RSA, which is based on the fact that factorization is hard on a classical machine? That is because we need the picture that I showed of 175 digits. Okay, so that would need lot of qubits. And as of today, the biggest machine that we have has only 127 qubits. So which means 2 to the 127 is how much you can go. Okay. This is not yet available to everybody. Okay. So therefore, there is a lot of research going on by cryptographers known as post-quantum cryptography, which does not use factorization. Okay? So, to build quantum computers, we need theoretical physicists and experimental physicists. And the computer scientists do the algorithm design and complexity analysis. And of course, computer engineers need to minimize the number of actual experimental gates, etc., so that, uh, as we know, that quantum technology is still very fragile, error prone, so that we can make good use of quantum computing to get reliable computation. So here is another interesting website, Timeline of Quantum Computing and Communication. And the
Uh, Ma'am, at least I cannot hear you. Uh, yeah. So
have I been inaudible for quite some time?
Yes,
no,
ma'am.
no, no.
I don't know, just
Just
10
like the
seconds.
last,
Yeah.
yeah, that just 10
Can you
seconds.
hear me now?
Yes, yes.
Yes,
Okay,
yes.
okay. So, so just take a look at timeline to find out what's going on. Different in communication, a lot of progress is being made for secure communication protocols, etc. So here are some pictures. Initial days, people were following ion traps, huge, and nuclear magnetic resonance. Ion traps are still being explored, and they have a lot of promise. Quantum chips, quantum dots. Okay. Um, and this is the superconducting processor of IBM. Okay, these are somewhat old. They are not capable of doing all kinds of quantum operations based on something called quantum annealing. D-Wave was a company which came up with this. They're still working on it. So there is a lot of work going on in this. Finally, one word of caution: quantum computing will not say that it can solve your NP complete problems, because it's a probabilistic way. Because when you are doing the measurement, there is the algorithm says with a high probability, the state you will observe, it corresponds to the correct output, but there is a non-zero probability of getting the wrong state. Okay, so these are known as bounded error quantum polynomial time complexity. So all the algorithms we have so far are here. Grover search tries to uh, NP-complete problems, the optimization NP-hard problems are search problems. So there have been some attempts, but that has not given polynomial time. Okay? So there are significant speed up, but the disadvantages are in constructing oracles or preparing the initial stage and the implementation error free. Technology is pressing on, and there are various methodologies, various types of design automation questions. How do I optimize so that I get error free operations? There are some things which has come up with. These are exact quantum algorithms. We are now looking at quantum approximate optimization algorithm. Given that there is some noise, which is a mixture of both classical and quantum. So let's stop here. I've exceeded my time. Okay. And
So, ma'am,
thank you for
there
your
are,
attention.
ma'am, so there are like a few questions.
Yes.
Swati is asking that could you please explain once again why Grover's algorithm will not be useful for things like integer factorization?
No. So, so to do the factorization, what will I do? I will search for factors by the oracle will do the division. Okay, division is polynomial time. But how many times you divide by the integers? So if your input is capital N, you divide by 3 all the odd integers going from 3 to square root of capital N. Okay. So these are the unsorted elements in your Grover search. So there are order of square root of n elements. And Grover search you will take square root of the number of elements. So that means capital N to the power 1/4. Now the size of these input which you are trying to factor, the size of the input capital N, that input will be represented by bits and it will take log of n bits. So for example, to represent 15, you need not 15 bits, but you need, the size of the input is not 15. It will be 15 if it was in unary or 15 ones, but we use binary. So therefore, it will take 4 bits, which is log of 15, ceiling of that. Okay. So, therefore, capital N to the power 1/4 is actually exponential of log of capital N. That is why using Grover search for Shor for factoring will not give you, will give you exponential time algorithm still. But Shor's factoring assures that you will get polynomial time. Am I clear?
Yes, Swati, please let us know in chat if this is okay with you. The answer is understandable to you, or you have anything else to ask. Shomodip, in the meantime, has two questions. The first is, are reversible computing in quantum implemented using Fredkin and Toffoli gates?
All operations are reversible. C naught, not Hadamard, rotation, any operation is reversible. I think this was covered in the introductory lecture.
Yeah, so Shomodip, if you recall from actually my talk yesterday, we showed that you can find out the gate which is of this exponential form, and if you take its dagger, okay, Shomodip is meaning reversible logic. Uh, yeah, okay. Yes, but as ma'am said that any quantum operation, any gate is unitary, and therefore you can always take its dagger, and U dagger gives identity. Therefore, every gate is reversible, and Fredkin and Toffoli are two examples of that, definitely.
As a matter of fact, till now, I don't think anybody has actually implemented Fredkin and Toffoli gates as primitive gates in any of the technology. We have only one qubit and two qubit gates. These are three qubit gates. So we decompose this in terms of available one qubit and two qubit gates to realize this logic function.
And maybe a last question from Shomodip again, that are optimization problems like combinatorial optimization also has a quantum speed up?
Um, Depends. If I mean, there are a lot different kinds of combinatorial optimization problems. Some of them do have polynomial time algorithms in classical, um, but if it is NP complete, then you don't call it quantum speed up. Uh, you may have some amount of speed up, as I explained that any optimization problem is a search problem, right? You're searching for the optimal solution. It may have many solutions, valid solutions, but you are trying to find the either minimum or maximum, whatever kind of optimization. So it's a search problem. So you might get speed up, but exponential, not necessarily exponential speed up. Then T equals NP would be solved with the help of quantum computers, which is very unlikely. Any more questions?
No, not yet. So if there are no more questions, if there are any questions that you have later on, please ask on Discord. We can always convey it to Susmita ma'am. And so if there are no more questions, let us all thank Susmita ma'am for this wonderful talk. And so the next session is Qiskit tutorial on implementing quantum algorithms on real hardwares and the challenges and scopes of that. And that will be presented by Dhinakaran. So Dhinakaran, can we also record your session as well?
So
Yeah, I
I'll
will.
leave the meeting. Thank you for inviting, and I wish all the attendees have a very pleasant tutorial by Dinakaran, an exciting one. Thank you.
So Dinakaran Vinayamurthy is a research scientist at the IBM India Research Lab. His research interests are in cryptography, blockchain, and quantum computing. At IBM, he has worked on algorithms for near-term quantum devices and projects around blockchain interpolability, zero-knowledge proofs, secure multi-party computation, and encrypted databases. He obtained his PhD in computer science, quantum information from the University of Waterloo and a master's in computer science from the University of Toronto. So, Dinakaran, on to you.
Okay. Yeah, thanks, Ritushi. Hi, everyone. We had a great intro and summary of quantum algorithms from Susmita ma'am. What I will do is I will uh, quickly open the Qiskit interface. Okay. Uh, you would have seen the Qiskit composer, right? Which is like share my screen as I'm speaking. Right. Yeah. So this is an interface that Qiskit or IBM Quantum has, where you can plug and play with different quantum gates, and then I don't know, start with your prototypes, right? The Qiskit composer. Of course, if you are if you want to write a serious program, and if you want to uh, yeah, have a more programmatic interface, it's called the Quantum Lab. And yeah, like you can either just go from here to open the same program that you wrote here in Quantum Lab and develop on top of it, or just directly go there to develop it, right? But today, the agenda for this session is simple. We'll just go over the Deutsch Jozsa problem that ma'am discussed, and then see how we'll implement that, right? And then while we do that, I will take you through some of the steps that are involved in going from a high-level computation to how it's executed. I'll first show it on simulator, the quantum simulator, and then hopefully if the hardware is like it's not queued up a lot, if at least one of the hardware is available, I'll also try to do a real hardware run and then see like the discrepancies that come up, right? Okay. Just to recap, what is the Deutsch Jozsa problem? We have a function f. We're given a guarantee that this function takes in n bits of input and output a single bit that is either 0 or 1, and that it's either a constant function or a balanced function. You would have seen the Deutsch problem, right, in detail. So Deutsch is like difficult. You have an n-bit input and then output a single bit 0, 1. And what does it mean by a constant function? Constant function means that f provides the same output on all its inputs. So the output can be either 0 on all its inputs or 1 on all its inputs. And what does it mean by a balanced function? Half of the inputs output 0 and other half of the inputs output 1. Doesn't matter which half. Okay. I mean, of course, f can be like totally arbitrary, right? We have an n-bit input. There are like 2 to the n possibilities for, I mean, if you have an n-bit input and a 1-bit output, there are like 2 to the n possibilities, right? Or 2 to the n possibilities of the output distribution or the type of function that can be. But here we are given this guarantee that f is either constant or balanced. Okay, and our goal, okay, we are given a black box access function. Our goal is to find whether this function is constant or balanced. You've seen the algorithm that I'm just described. The graphics are slightly different, so maybe I'll just go over it again. We'll have an n plus 1 qubit. So if the function takes an n qubits, we'll have an n plus 1 qubit initial state where the first n qubits are 0 and the last qubit is an ancilla. The first step is just applying Hadamard transform on all the qubits. I mean, another way of looking at this, we have Hadamard or equal superposition of all states as the first register, and then the minus state in the second register. But yeah, we can start with the 0 and the 1 and then apply Hadamard on all. And then the second stage is applying, just passing through the oracle, right? Oracle for this function f. So what do I mean by the oracle? So this particular oracle is something where we'll take an n qubit input x and this 1 qubit input y, and this retains the first n qubits and outputs it, and the final qubit output is y XOR f of x, right? Oh, sorry, if it's a binary thing, it's XOR, but you can think about the equivalent in the qubit space. But here, this particular what we call as an oracle here, it takes in the n qubit and then retains the input, and just the last ancilla qubit, it sort of encodes the function output along with it. So this is, I think, one natural way of constructing a black box access to this function. We'll see how to efficiently implement this also. But just to go back to the high-level steps of Deutsch Jozsa algorithm, the quantum algorithm, will pass on the state that's obtained from the Hadamard, like the Hadamard to this oracle. And then the second stage is we apply the Hadamard again on the first register of the n qubits, and then we measure it. And as ma'am mentioned, if we get all zeros, in the first 10 qubits is a constant function. If it's not all zeros, just to what the output is, it's a balance. Okay, I'm not going to go through the derivation again, but just a recap, right? So, okay, maybe you'll just go back this, and then maybe I'll add. Yeah, okay, let's just do this. So we'll have a 4-qubit state. We'll have used the n, we'll have n equals 3, right? So 0, 1, 2 are the input qubits, and let's treat Q3 as the ancilla. Or maybe I'll just do 1. Yeah, so Q4 is the ancilla, and 0, 1, 2, 3. Let's say n equals 4. Okay, if you don't remember this interface again, yeah, we see the state vector, the corresponding state vector corresponding to this. So by default, in quantum hardware, we start with it's an all zero state that we start with. So you can easily see that the state that we here is have is all zero state. This is the probability distribution of the states. So this is the exact state vector itself. So you have amplitude, right? This is the probability distribution on, yeah. And then this is the code, but I think for this rest of this lecture, I'm not going to play this part. All right. So what did we have here? We want the initial state to be like all zeros and one. Okay. So this is the graphic for an X gate. This will convert the ancilla qubit from the default 0 to 1. So as you can see, you can read from the LH. Yeah, the LHB, the least significant, the most significant bit of the least significant bit, I think you can go from left to right. So that's from Q4 to Q0. Okay. So here the X gate transforms the all zeros to 1 for the zeros, just for the ease of visualization. I'm going to add a barrier. I mean, there's no quantum operation here, it's just ease of visualization here. All right, so the next step is applying the Hadamard on all the qubits. By the way, I think you guys have done some experiments before, right? So you can also open this on the side and try it yourself. Okay, so I just applied Hadamard on all the qubits, and I will create another barrier. Right, so this is the initial state we start with, like all zeros followed by a 1, get 0, get 0, get 0, get 1, and then bit of advance. Right, so that's what we have at the end of the space 1. And right, so what do we expect? I mean, if we just, let's say, forget this X gate, right? If you just apply Hadamard on this, it should be an equal superposition of all possible states. And then now if I apply the X gate again, it's like almost the same, except that the phase is flipped for whenever the last qubit is hit. Okay, so the next step is applying the oracle. So what does it mean to construct an oracle where for a particular function where it retains the first 10 qubits and then you just flip the last qubit to what it, right? I'm not going to go into a detail like a generic construction of an oracle. We'll first see simple construction, right? So we'll just try to do one for a constant function for a balance. Okay. So before I tell, right, just think about what would it mean to construct an oracle for a constant function f where the output is always 0. So what does it mean is f of x is 0 for all x. Okay? So that's essentially this value is 0. Y XOR f of x is 0 for all x. Right? So u of f on input x and y will just output x and y. Right? So that's like an oracle for a constant function where f is outputting 0 for all the x. So essentially an oracle for f equal to 0 is not doing anything. It's just the identity operation, right? And like similarly, an oracle for f, where f is like outputting 1 on all the inputs x. So that's essentially like x will retain as x, and then f of x is 1 all the time. So it's just y XOR 1, which is just flipping y, right? For a, if it's a qubit, it's like either 0 or 1. So 0 XOR 0, sorry, 0 XOR 1 go to 1, and 1 XOR 1 will go back to 0. So it's like an x gate operation, right? So if you have to construct an oracle for function f that outputs 1 on all the inputs, then it's again like simple to construct such an oracle. We'll leave the first 4 qubits to identity and just uh, apply an X gate on the last qubit. So what we'll do now is we'll first like do this, not just apply identity operation, and then see if the result is what we expect, right? So what do we expect? We expect an all zero output because it's a constant function. So I'm not applying anything here on where the oracle is supposed to be. And then the next step is I apply the MARD on the data qubits. Sorry. And then just measure. The first 4. I mean, all data qubits. Okay. So what you can see is the state vector is probably like more precise way of saying it, right? So what you can see is it's always the first 4 qubits are always 0, right? This is the last qubit which can be 0 or 1 here, but we don't care about it, right? So what Deutsch algorithm says is that if the first on measuring if this is always 0, I mean, of course, I just did a single run, right? I mean, if you just look at this, right, this will just say for a single run. But, oh no, this is already for 0. Right, no, even this is fine. But this gives the exact state vector that we want. So the ancilla qubit is ignoring the ancilla qubit. All the qubits are always 0, right? It's 0 with probability 1. We don't have any non-zero probability for a state where any of the first qubits are non-zero, right? So this is as expected, right? Any questions already?
No, there are no questions yet. So,
Okay. What I will do is I'll just go do a quick run through of the other variants of Jozsa before I will tell a little bit more about what's happening in the backend to go from like some gates that we put in here to how we get the results, right? Okay, the next is if we apply a function. Oh, okay. What is the ancilla qubit? Okay, there is nothing fancy here. It's just something additional to what we have in the data qubits, right? That is something we use in a quantum algorithm to, I don't know. Okay, very informally speaking, you can think of it like something used for a rough word, right? It's not an actual calculation, but it's an extra state that you keep to uh, make use of it, and then like sometimes transfer some state, and it's something additional to the actual the qubits where you store the input to the actual algorithm, right? Any additional qubits that you use. That's what we say as answer. Sorry, Ritaji, you going to say something?
No, no, it's okay. I was just going to read out the question. That's
Ah, yeah, this popped up, so this notice. Okay, so all right. So the next thing is
so just just there is one. I think this is a related question. Shomodeep is
okay.
asking: is it possible to design the oracle without using the ancilla?
Uh, I think the way we define an oracle. Okay, so first of all, as we discussed in the earlier part of this lecture, on I assume also in the first day, right? All the quantum operations we expect it to be reversible, and if you want to make so uh, let's say if you want to construct a way for computing this function f such that you want it to be reversible, then you have to have the output of this function be captured in some additional state that you have, right? And even that has to be reversible. So for that, it's mandatory to have some additional qubit because like the input x has to be retained, right? If you make some changes to it, there is no guarantee that for an arbitrary function f, there will be another operation to invert it back. So I think it's sort of necessary to have an oracle just to retain this reversibility property. I don't remember if there are any other uh, reasons for it, but at least this is one strong reason where it's necessary to have the answer. Okay. So the next, yeah, we'll also try for the constant function where f is always equal to, I mean, f outputs 1 on all the loops. Okay. And as I mentioned before, it's just applying the Qiskit. Okay, so I've not applied it, but even after applying, what we should see is that the first 4 qubits should measure to 0 with probability 1. Okay, so even after apply, I mean, we see some state, like minor change in the state vector, but what we expect is what we get. We have the first 4 qubits as, I mean, being 0 as the only possible quantum state, and there is non-zero probability. There's no state where one of the 4 qubits is not 0 has a non-zero probability. So this is again as we expect. Okay. Next, we'll try to construct an oracle for a balanced function. I mean, there is no single way of doing this. This is just one trivial way of constructing an oracle for a balanced function. And hence, yeah, the effort here is not to try to have a general way of constructing oracle for balance. This is one example. We can just do a sanity check that this is an oracle for a balanced function. So what this oracle does is it takes, it's like almost like a parity function, right? So it outputs 0 if all qubits are 0. Okay. Trying to have a general way of explaining this. So I think if you have, there are like, yeah, so if there are even number of qubits, even number of ones, then you get a 0. And if there are odd number of ones, you get a 1. I think that already like separates the all possible states into like half of them outputting 0 and half of them outputting 1, right? So this is like one example for a balanced function, and this is the oracle for it, right? Okay, so what I will do is just, and then I will just okay, I'm going to enter the last qubit, but what we should expect is, yeah, the states that we obtain should have something other than 0. I mean, here it's all ones. So it's not as, I mean, always, right? I mean, the inverse of all zeros is, I mean, we can call it a balanced function, even if there is some non-zero probability for some other state to have one of them, where one of the qubits is 1, and one of them measures to 1. But here it just so happens that all of them measure to 1. So this is what we expected, right? Before, if we have a state with one of the qubits measuring to 1, then it's a balanced function. Of course, given the guarantee that the function that we start with is either balanced or constant, right? So since we have this guarantee here, even if like we were, so this is supposed to be a black box, right? Of course, I'm showing it here for the demonstration. But even if this is, yeah, if a quantum algorithm is not aware of the exact gates that here, right? So the algorithm is just this, the left, whatever is to the left of this, and whatever is to the right of this, right? What's present inside, like we don't have any gates outside, right? So we can replace this with some oracle for an arbitrary constant or a balanced function, and the output is will still be like what we expect, which is it will be zeros. I mean, constant function are only 2 possibilities, but for any balanced function that we come up with, we'll have the output state to be to have a non-zero probability for at least one of them. I should include zero, non-zero. Okay, so that's about it for like the direct explanation of the Deutsch or just running of the Deutsch Jozsa algorithm. What I will do is, okay, so right now this is all run on the simulator. Okay, what I will do is I'll just run. We are lucky. So this machine has just 10 jobs. I will hope that we run. So what I will do is, what I'm doing here is, I'm just running it on one of the quantum systems that we have, and then I'll try to, I'll go over some of the steps that are running in the that happens in the background, and hopefully by the time it finishes. But even if it doesn't finish, I have some prior run where I can show the results. Okay, so we are running it for a balance function. Okay, so while that's happening, okay, what we provide here is a set of quantum gates, right? And like ma'am mentioned, there are some popular quantum gates, and like we don't know whether they're demonstrated on quantum computers. The reason is that when we build the hardware, there are a set of constraints that each hardware has, right? Depending on the underlying, like the basic technology that's used for building the qubit, and different, like a ton of engineering constraints that come up when we try to like build mechanisms for controlling the qubit, like for applying single qubit gates or 2 qubit gates or measurements or whatever, right? So the hardware team, they come up with a set of gates that are native to the hardware that they feel more comfortable controlling than rest of the gates, and also trying to like make it universal. That is, any arbitrary computation that we write here should be convertible into some sequence of the basis gates that you were in, right? So if you have seen, like you remember from your like first year courses, digital principles, so you've seen the NAND gate and NOR gate, right? So those are universal for the classical hardware, right? So if you have a NAND gate, any arbitrary computation can be broken down into a sequence of NAND gates. Or I think the XOR gate and let's say XOR gate and yeah, I think and XOR are also universal, right? So that's not equivalent to a NAND gate, but that's another sequence of I mean set of gates that are universal for the classical hardware. And you would have heard of compilers that takes in, let's say, a Python program, and then okay, maybe Python has many interpreted. Let's say C++, right? You write a high-level C++ program, and then that gets converted into a set of instructions that a machine can understand, right? In fact, we have multiple levels of uh, like compilation, to use it loosely, right? I mean, we can convert it from a C++ program to some x86 instructions, right? You like heard of these x86 instructions that are native to the Intel hardware, let's say. And I'm assuming like even further down, if you go even like further down into detail, each instruction will be some set of pulses or whatever that's at the hardware level to control the ICs, or that's like that form the basis of computing, right? So there has to be like compilers to convert any high level program that you write into the instructions that machine readable, the machine can understand, right? It's not good to make it equivalent, right? So in quantum world, even here, this is not like a very high level program, right? I mean, if you go to one of the Qiskit tutorials, let's say like for finance, right? The program that you write will be very similar to like a Python program, right? Like you import some certain libraries, and then yeah, I mean, this is you have some certain functions that you run and different I mean, like if you look at it, you don't know whether it's a quantum program or like something. It just looks, like, at least visually, like yet another Python program that you write, right? This is a level below because I'm just dealing with gates. I'm not talking in terms of this high level function. Uh, but the thing is, even this is not something that's native to hardware that's understandable to hardware, right? So irrespective of whether you write something like this or whether you write something like this, Qiskit had what's called a transpiler to convert this input circuit, or even something at a higher level like this program that I showed here, into a set of instructions that is understandable by the hardware. Okay. It does a variety of things. Okay. There are like many things to do. First, some are similar to what you would do in classical hardware, but some are very specific to the quantum hardware technology that we have. I mean, it ranges from circuit optimization, like where you just do some basic, simple optimization checks, and then they call this a three plus qubit gate decomposition. So here, I think in this program that I wrote, I just wrote single and two qubit gates. But let's say, yeah, this is a three qubit gate, right? So this involves gates 0, 1, and 2, right? So, but natively, almost all the hardware. Let's look at this. So, like, if you, this is our public information, right? So if you go here, so these are it's a 27 qubit machine. I think Kolkata is a 27 qubit machine, and uh, this just gives the connectivity of the different pairs of qubits that you have. So, right. So we just try to implement single and two qubit gates in this. And I mean, if you go here, there are like a variety of details that you can find about this. That's beyond the scope of this lecture. So one thing that the transpiler does is breaks down a three qubit gate into a set of 1 and 2 qubit gates. And then the next thing to do is here we write a program saying, okay, Q0, Q1, Q2, Q3. But it need not be the case that this Q0 is mapped to this qubit 0 that's in this machine. right? Or similarly, I mean, I ran something on Windows. It's a similar architecture. It should not be the, I mean, it need not be that 0 is mapped to 0, 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. Okay, here. Because there are like different constraints that have to be looked at, and it's much better if there is something smart that's thought about to see where the qubits can be placed. Okay, and so on, right? And at some point, as I mentioned before, the basis gates for a particular hardware, maybe that's some. So for some of the, I don't think this is, it in fact varies for different hardware devices, but these are some set of basis gates for one of the IBM quantum hardware. So ID is just identity gate, RZ is rotation in z-axis along z-axis. We have SX gate, X, and CX, right? It's an exercise where you guys should think about whether it's why it's a universal set. I mean, first you think whether it's a universal set and then see why. But it takes, but what we wrote here is like, I'm calling it this a Hadamard, and this is, okay, this is CX. So CX is fine, but like Hadamard is not there, right? So one of the steps in Transpeller is converting this gates that we do. I mean, let's say if I'm using like all these gates here, right? Hadamard, sorry, not all of them will be basis gates, and it takes an effort to convert them into a set of basis gates. And also, there'll be a lot of circuit optimization needs to be done. One intuitive thing I can say is, okay, so the color here sort of represents the extent of noise that's there if you want frequency, right? Let's say, yeah. So this sort of says how stable a particular qubit is. Okay, higher, I guess, yeah, the more violet it gets, the better it is. So, uh, so I think it is very useful to have a compiler that is aware of the imperfections in the hardware, and especially if you want to do a single qubit gate, each of the qubit also has its the gate errors that it has, and it's very useful if there is a compiler that understands these constraints and then tries to make a best placement of the qubits that we have and also the gates that we want to do with respect to the hardware that we have, right? And place it in the best possible way. So that's one of the things that the circuit optimization does. And of course, it also tries to simplify it and like do something more fancy. But this is intuitively, at least, these are the constraints that it has to overcome, right? Yeah, I mean, they try to do some scheduling, so on. But this is essentially the different set of things that a transfer is. Maybe I'll try to go back to see if the hardware.
Hi,
Yeah.
Dhuna. So there are two questions in the meantime. Swati is
Okay.
asking that in IBM system configuration, what does C0 error and average readout error represents?
Yeah. So C0 error essentially gives you the. So let's say we have a 2-qubit gate between 0 and 1, right? C0 error sort of quantifies the extent of noise that you can expect when you do a C0 operation in between them, informally speaking. So that's for the C0 error. And a reload assignment error means, okay, let's say, wait, I think, is it the union of these two typically? So at least let's talk about this, right? Probability of measuring 0 prep 1. So this means that let's say we have a 1 state and what's the probability of that measuring to 0? And inversely, we have a 0 state and what's the probability of measuring this to 1? And I'm assuming the reload assignment error is sort of the union of these two. I don't
Okay,
have it off the top of my head, right? That's correct, right, Ritaji? What do you think?
yes, that's correct actually.
Okay. Yes. Yeah.
And Mohua is asking, I am not sure about this, how XX gate can be implemented.
Maybe asking about swap because it looks like access. Is
Uh,
this the gate that you're asking about?
So Mohua is a, or I can try to like unmute Mohua and she can ask it herself only. Just a second.
Yeah, otherwise, if it's just two X gates, then I mean, these are both single qubit gates and you can independently.
Am I audible?
Yes, yes.
What is the, please explain me what is the difference between the implementation of X gate, means how that can be implemented within this interface, X gate and XX gate. What is the difference between them and how can that be implemented?
Okay, so this is an X gate. Okay, I mean, it doesn't look like an X here, but this is the X gate. Okay, this converts, just create a new file and show you, right? So what this should X do? It should convert Ket0 to Ket1 and Ket1 to Ket0. Right? So here it just converted like all zeros to 1. So this is the X gate. And I don't know if X by XS gate you mean first of all, so X I don't think there is an XX gate unless you're talking about applying an X gate to two different qubits. And this just really generalizes because there is nothing special. It's like independently applying an X gate to two different qubits. So 0, 0 became 1. And X gate again to convert the first qubit to 0, back to 0. Yeah. Does this answer your
Is this
question?
the tensor product between two X operations? XX.
Sure, yes. Yeah. If you talk in matrix form, yes.
Okay. Okay. Thank you.
Oh, wow. Some of this you have not seen it in recent times. What is RXX? Where did you see it? Oh, okay, it's here. Is it just RX or oh, it's like a controlled RX. Sorry, I have to look at the documentation myself. It's been a while since I looked at
So
these.
I think the at least RZZ is like e to the power I theta ZZ. So RXX should be e to the power I theta X tensor X. It's supposed to be a parameterized X, the gate, where it is like X on, it is a rotation
Yeah,
around X on both the qubits with some particular parameters.
yes. So, oh, by the way, I mean, if you want to do, you can. What I did was I just double clicked this gate and then looked at the information and then just did a reference. So, yeah, I think it's what you said. You're right.
Yeah.
Thanks. Uh, yeah, I'm assuming you can similarly explore what's RCCX and RC3X.
Yeah.
Right. So here, hold on, this is quite nasty. Okay, so what did we run? What was, I'll just show again. So this is one of the things I ran on a hardware, right? Uh, this is like a 5-qubit operation. Okay, let's see what it's like. So here we just applied a header mard and then a set of C knots and then a set of header mards again and then the measurements. Okay, before we look at the results. Yeah, okay, sorry. This is the circuit that we compile. And this is how the transparent circuit looks like for this hardware. And I don't know why, but for some reason, it shows the first 5 qubits and we didn't try to choose any of the other. Okay, but it need not always be the case. I think I have some run from this past week. Yeah, so this is the same thing done on 3, excuse me. This was done on IBM Cube Kolkata. Here, it did not use the first 4 qubits. It just used some set of arbitrary qubits that are connected to each other that wanted the best to run. But yeah, here it used the first 5, and yeah, it converts an H to an RZ, so it's RZ, and then a set of like qubits like this, right? It just transpiles it to this. I don't know whether I can really give an identity that just goes from here up top of my head. But oh, okay, it might also need to do some swaps in between. The reason is, so here we are expecting this 4th qubit to be connected to Q0, Q1, Q2, Q3. But yeah, but we do not have any any qubit in the hardware which is connected to 4 other qubits. Okay, the heavy hexagonal architecture that the IBM quantum hardware, almost all the devices in the recent past and all the planned devices in the near future, they'll all be using this heavy hexagonal architecture. What that means is essentially like plays like a hexagon where you have qubits on the edges, on the nodes, and also on the edges of the hexagon. Okay? That's why we call it the heavy hex. And yeah, so here we'll only have a qubit that's connected to 2 or 3 other qubits. Right, the degree of a particular qubit will be 2 or 3. So since there cannot exist a qubit that's connected to 4 other qubits, which is what's required for Q4 here. Okay, in fact, okay, they did do some change. So I think the Q4 is mapped to Q0. But yeah, so still we don't have any single qubit that's connected to 4 other qubits. So there'll be some swap operations done in between to properly execute all these 4 synods. Anyway, so that's one of the changes that's happening here. And then, of course, yeah, as I mentioned before, conversion of NMR to the basis gates. Yeah, I guess those are the 2 prominent things. And of course, something happened in the background in deciding which 5 qubits were chosen for Q0 to Q4. And this result is quite noisy. Okay, because if you remember the ideal output, if you remember, was uh, just like 0, 1, 1, 1, 0, 1, 1, 1, 1, plus 1, 1, 1, 1, 1, right? Yeah. So 0, 1, 1, 1, 1, and 1, 1, 1, 1, like equally like powerful. So these are the 1 over square root 2s, or yeah, 1 over square root 2 is like 0, 4 ones and 1, 5 ones. So this is the state that's supposed to be there. But then what we see here is something like this, which is because each hardware has its own set of imperfections, and then given that we have a lot, it's a like high depth circuit, right? High enough. So we have like a lot of CNOTs, a lot of 2-qubit gates. And as you see there before, there are like 2-qubit gates with a decent amount of error. So if you just do a lot of them together, it ends up being this as against just 0, 1, 1, 1 plus 1, 1. Oh, by the way, this what you see here is I just ran this 1024 shots. What this means is I ran the same circuit 1024 times, and this is the distribution of the outputs that we got after we measure the first 4 qubits. Maybe one of the older runs will give something slightly more promising. So here it's a very similar circuit, but it's run on 1 less qubit. But what makes it so different from the previous one is that it doesn't have a swap, right? Because there are qubits that are connected to 3 other qubits. So it was easy for it to take one such qubit that is the least noisy. And hence, this is like much less noisy than the previous one, right? Because here the correct answer was 0,111 and we got 0,111. So almost like 92% into an. And yeah, it might get too late if I just try to run something else with 0,0,0 for a constant function. I think this was something that's run for a constant function. I'll just quickly show you the results for this. So even here, yeah, so this is a constant article as the identity function. And yeah, no surprises here. And here, of course, it's even less noisy. Okay? It's almost 97% accurate. Yeah, because here the expected answer is the non-noisy version output 0,0,0,0. Here, it's almost right. So yeah, that's mostly about the content that I want to show, unless one of you want to get into some more detail of one of these things.
Okay. Yes. Orpita is asking that, sir, as we see in the output that the other probabilities are also high, so can we take this result to be okay?
Okay, so this is what we got, right? So as long as it's dominated towards, it's closer. Okay, I don't think there is a generic answer to this question. Okay, it's just for the problem that we are trying to run here. We know that we should either get a domination for all zero output, right? As long as all zero is not dominating, I think we can somehow trust this. Okay. I mean, ideally, I would have wanted to show that okay, a very deep circuit that will also output noisy here. But the thing is, just Deutsch algorithm just so happens that all zeros happen only for a constant oracle, and both the constant oracles will not lead to a high depth circuit. So it's not possible for me to run a circuit with a lot of gates where the expected answer is all zeros to show that that will be prominent and the other ones will be less. I mean, like have less probability. But here, maybe it's okay here because all zeros is like the probability for an all zero vector is like very less compared to the others, right? So I think we can reasonably trust it. But let's say if you were to run a like a very miniature version of Grover, right? That's where your real question will come in. We have to run it to see how it is. But yeah, I mean, this is all visually speaking, right? Of course, there can be some noise mitigation techniques that can be applied, and also other than that, for a specific problem that you're looking for, there are certain level of like noise that you can tolerate, right? Like for here, like I mentioned, uh, as long as all zeros is has like less probability, we can trust this. And for this a problem specific answer. So maybe for some other problem there is a similar thing you can come up with, right? Noise mitigation and then like evaluation based on that. But
Also,
quantum computers are inherently noisy, so that you will get a noisy answer. It's just about uh, figuring out what's the best way to extract our answer from the noisy results. Yeah, sorry, Chris. You want to add on something before the question?
No. So actually, Lakshmi Prasad Nayak had hand raised, but I don't see you asked. You haven't asked me question in the chat, and somehow I cannot like unmute you or something. So if you have a question, can you please write it in the chat, Lakshmi?
Okay, so while he's doing that, are there general techniques for constructing oracles in sense of okay, so if you're interested in quantum algorithms and running in the real world problems, I would ask you to place less emphasis on oracles because the main reasons that the theorists came up with the notion of oracles is to prove the power of quantum computers. I mean, theoretically, prove the quantum power of quantum like algorithms or computers over the classical counterparts. So there is this notion in complexity theory called like oracle complexity. What that essentially means is that uh, I mean, going just taking a step back, in complex theory, the goal is to see, I mean, separate complexity classes, right? There will be a class of functions that can be run in polynomial time. There is a class of functions that can, whose answer, given an answer can be verified in polynomial time. There's a class of functions which needs uh, like space that's logarithmic in the size of the input to run, and so on. So the goal of complex theory is we try to separate these complexity classes or prove that they're almost equal, right? And it's very hard to do, and you'll be very surprised to see the amount of things that are actually proven, right? Most of the things are just what you believe, and they take multiple approaches to separate classes of functions, and one of the approaches that we take is oracle based separation. Okay, so what they will do something similar to what we did here. They will assume existence of an oracle to a particular function or a class of functions, and then they will say that, okay, so this other I think I had a take, I don't know what it is. Yeah, let's say like they both, let's assume that there is a linear program solver oracle, right? And then we are trying to say that solving a system of linear equations uh, is different from a set of algorithms that's solving the graph coloring problem, right? And like if it's easy to solve set of linear equations with access to the oracle quickly, and if it's not easy to solve the get of the graph coloring problem with this oracle quickly, at least we can say that, okay, these two problems are like not as equally easy or equally hard, right? Because let's assume that this is a set of problems that we cannot prove easy or hard directly, and hence we just assume an existence of an oracle and then try to prove the equivalence between this set of problems or the non-equivalence between this set of problems. And that's the reason, when quantum computers came up, people tried very similar approaches to prove that quantum computers are hard compared to classical algorithms, or like they want to prove that quantum computers are exponentially faster than classical, right? Or probably faster in some form. And that's where the oracles came in, right? And in a real world algorithm, you won't really see a use of an oracle. So in that sense, I would suggest you to not pay too much attention to the oracle. But since Deutsch is a simple algorithm, it's one of the classic algorithms. I still like went ahead and like showing that and then demonstrate uh, the implementation of an oracle. Because okay, so next question: the other probabilities are also in the output, then yeah, okay. I think the short answer is you have to study the field of error mitigation. So there are like a lot of error mitigation techniques uh, that exist to do that. It's not something like trivially that you can say in like a few words or a few sentences. But I don't know. Intuitively, some approaches are like you just run a particular circuit. Okay, let's try this. So there is one approach where you run this circuit once, and then you sort of run, let's say, this particular circuit 2 times, and then see what the output is, and then try to run this circuit like 4 times and see what the output is, and so on. And then that gives like an extrapolated error. And after a certain number of runs, you try to sort of do like an equivalent of polynomial interpolation, like some interpolation back to a non-noisy like run of this circuit, right? That's one approach that people try. And some other approaches, like here, one of the causes of noise, okay, maybe that's something to be looked at, right? There are different reasons why noise happens. One is that due to the imperfections of the gate itself, uh, and like predominant most of the time 2-qubit gates are more noisy than a single qubit gate. So if at all you could come up with a way to find an equivalent version of the same algorithm that you want to run with minimal number of 2-qubit gates, and maybe you can even have a more single qubit gates, that's one way you can minimize the noise. Or another source of noise is idling of qubits, right? I mean, it's like one thing that you can not imagine unless you look at running things in the hardware is that if a qubit is idle for a while, it will attenuate. I mean, there are different kinds of things that can happen to the qubit, more to take it away from its original state. Okay, so one of the things that the researchers have studied is filling some of like an identity, gates that are equivalent to identity, such that the qubit doesn't remain idle for more than like, I mean, such that it's not, it doesn't get noise, right? Of course, there is some noise that comes up when adding a gate in itself, but there are some set of gates that you can add such that it prevents some idling errors, right? And sometimes in classical compilers, I mean, compilers for classical computers, one of the very popular approaches is it's called an ALAP scheduling, as late as possible scheduling. So they always try to apply a gate as late as possible, right? Unless that particular bit needs to be acted upon, they won't apply that. Okay. Yeah, like here, right? This Hadamard gate. I mean, we could have applied this Hadamard gate here, right? So if you give some equivalent of this to a classical compiler, it would have it. It knows that there's a measurement that needs to be done here, and hence it would not apply this Hadamard till just before the measurement. Okay? And maybe also you can do this for some similar thing. But in quantum, it's not helpful because there is noise due to idling, right? So people also try to come up with better schedulers to do that. And there are more fancy, like fundamental quantum-based approaches that try to mitigate noise. So there are like a variety of things that you can do to mitigate noise. That's one type. The second thing is you can also try to do some post-processing, right? You know what particular program that you're trying to run. So you can try to see from the noise distribution and from your circuit, try to have some model of the noise in the hardware and try to sort of invert that noise based on the model that you create and do that. So there are like different varieties of things, approaches we can try, and that's a interesting like a domain in itself and an interesting research direction. Any other questions?
Yeah, I don't see any more questions. So if there are no more questions, we can thank Dinakaran for this wonderful session, and I can stop the recording.
Yeah, have a good rest